video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises. In this series of video library modules dealing with well completions, we have already discussed the routine procedures necessary to prepare a well for production. It is important to recognize that in some areas of the world, a fracture stimulation treatment is a critical part of the completion procedure. Whether considered as part of an initial completion or as remedial treatment for older wells, the success of fracture stimulation is very impressive.
It is estimated that over 25% of the total reserves in the United States, over 8 billion barrels of oil, would never have been commercially recovered without hydraulic fracturing. Many areas, such as the Middle East, where the wells are highly productive, have not yet found a need for widespread fracturing. But at the current stage of development in North American reservoirs, perhaps 35 to 40% of all wells completed annually are fractured. In some cases, the fracture treatment is required to achieve economically acceptable rates of flow.
Successful fracture stimulation treatments increase ultimate recovery by improving the productivity of individual wells, allowing them to produce at higher rates and extending their economic producing lives. Fracturing also permits a reservoir to be efficiently drained by fewer wells, improving the development economics of the area. Reservoirs with an effective permeability of less than 1 millidarcy are generally considered the most likely candidates for successful fracture stimulation treatments.
Generally speaking, successful treatments have increased production rates from 1.5 to 8 times the pre-frac production rate. Increases can be even greater, particularly if the well also has significant near wellbore damage. In this module, we'll first discuss the theory behind the basic concepts of fracturing. Then we'll outline the preliminary investigative work that should be considered when evaluating a well for a fracture treatment. We'll look at the details of a good fracture treatment design that should be considered once the decision to frac has been made. We'll visit a fracturing treatment location to see its execution. And finally, we'll discuss post-frac evaluation techniques. Your manual includes additional material that you'll find helpful in understanding the concepts illustrated in this video.
The objective of a hydraulic fracturing treatment is to create a highly conductive, continuous flow path extending from the wellbore. This is accomplished by driving a fluid wedge through the low permeability rock. A fracture is typically in a vertical plane, and wings of the fracture are 180 degrees opposite one another. This induced fracture can retain its high conductivity by placement of a propping agent or by dissolving the formation rock with acid.
The high conductivity of the new fracture, defined as its permeability times its width, reduces the amount of energy required to flow oil or gas through the formation to the wellbore. Induced fracture widths are believed to range from approximately 1/10 to 1/2 inch, with a majority of tests indicating that 1/10 to 1/4 inch is most common.
The fracture length required to achieve a particular degree of improvement in flow rate depends on the formation permeability. Typically, a 200 to 500 foot or 60 to 150 meter fracture extension on both sides of the wellbore is adequate. Lower permeability rock requires a greater fracture length. Thus, fractures extending 2,000 feet or 610 meters on both sides of the wellbore are created in some tight gas reservoirs.
In higher permeability zones, the fracture length may be shortened and the fracture width increased to achieve a high fracture conductivity without a long fracture, good for bypassing formation damage found in such zones.
The conductivity of the created fracture is often 100 to 10,000 times the formation conductivity. If the fracture conductivity is not significantly greater than the formation conductivity, then the increase in production may not justify the fracturing cost. It is for this reason that undamaged high permeability wells are not fractured.
A fracture is initiated by applying hydraulic pressure to an exposed formation. Injecting at a rate above the ability of the exposed rock matrix to accept this fluid will increase the formation pore pressure at the well bore. When the pressure exceeds the tensile strength and stress load on the formation, the rock will rupture. The fracture will continue to enlarge until a barrier is encountered. The treatment is stopped, or the injection rate falls below the rate at which the fluid is leaking off into the formation.
Barriers and other conditions that limit the geometrical growth of fractures include rocks having a higher tensile stress, higher stress loading, or stress loadings oriented in a direction different from the formation being fractured, faults that dissipate fracturing energy, or a buildup of proppant at the bottom of a growing fracture. Usually, we do not know the relative importance of these factors, even qualitatively, and efforts to predict the geometry of induced fractures with computer models will continue to be challenged by this fact.
An estimate of fracture orientation is the first step. If we visualize a portion of the reservoir rock, we realize that in order for a fracture to be formed, rock must be displaced. The direction in which this is most easily accomplished is the one having the lowest stress loading, and so the fracture will be oriented perpendicular to this stress.
In most areas where tectonic activity has not drastically increased the horizontal stress environment, the overburden stress, usually about 1.0 psi per foot, is the greatest stress on the rock. Consequently, at the depths where most fracturing is done, the induced fracture will be vertical and perpendicular to the least principal horizontal stress. However, in certain areas where geological stresses have not been dissipated, or at shallower depths, the orientation of the fracture may be inclined, or possibly close to horizontal.
The geometry of the fracture must be predicted in order to project the improvement in flow rate. Modeling a fracture treatment allows us to optimize the design to ensure the best economic results. But we require accurate data to make the application useful.
A common method of gathering design data on the formation is to perform a mini-frac, a pre-fracture treatment injection test. Pressure and injection rate are carefully recorded and used to determine minimum in situ stress, fracture gradient, leak-off coefficient, and treating pressures. Using this data, a mathematical model can be chosen that will help in the design of the major portion of the treatment.
Two commonly used mathematical fracture models are the KGD model, after researchers Kristonovich, Zeltov, Gertzma, and Deklerk, and the PKN model, after Perkins, Kern, and Nordsten. The basic concepts of these models differ from one another, but both have been substantiated by field data and are believed to be simplistic mathematical representations of what might take place during a fracturing treatment.
The KGD model assumes the fracture height is constant and does not continue to increase during the treatment. The fracture width is the same from top to bottom and tapers to 0 at the tip. During the course of a treatment, the fracturing pressure reduces at the well bore as the fracture extends away from the well and increases in width.
The PKN model also assumes the fracture height is constant, but the surface of the fracture face is slightly curved, with the fracture width greatest at the vertical midpoint. During the course of a treatment, the fracture pressure at the well bore increases as the fracture extends away from the well, unless uncontrolled growth is experienced. Currently, most computer design programs are based on such two-dimensional mathematical models, which must be given an assumed height to solve for the fracture length and width.
This estimate of fracture height may be the most important single factor in the design of any fracture treatment, and also the most difficult to determine. Using this height dimension, a fracture length and width can be calculated from the appropriate model. The difficulty in determining the fracture growth pattern, including the height, is due to the variety of rock properties affecting the fracture geometry.
For example, the fracturing gradient is a measure of the unit pressure required to hold open an induced fracture, normally expressed in psi per foot of depth. This gradient can be calculated if overburden, pore pressure, Depth and a reservoir constant are known. The actual fracture gradient is normally calculated from pressure measurements taken during the pre-frac test and considers factors such as formation depth, surface treating pressure, hydrostatic pressure, and frictional pressure losses in the pipe and through the perforations.
Increasing the pore pressure to the point where the tensional stress limit of the rock is exceeded initiates a fracture. If the fracturing fluid cannot penetrate the rock matrix effectively due to the use of a non-penetrating fluid, plug perforations, or plug formation, for example, the breakdown pressure will be significantly higher. This is because the surface area on which the pressure is allowed to act is considerably smaller, even in an open-hole completion.
For this reason, acid is often spotted as the fluid for initiating the fracture, especially in newly drilled wells where damage may be significant. The need for a penetrating fluid to initiate the fracture without abnormally high pumping pressures cannot be overemphasized. The fracture initiation is followed by a volume of low leak-off rate pad fluid. Then a viscous proppant transport fluid is pumped and followed by a non-damaging fluid to flush the proppant-laden fluid from the wellbore. The fluids used to treat the well must then return to the wellbore without restricting subsequent reservoir fluid flow. Each of these activities requires a fluid with different properties. Pumping the correct type of fluid in the correct sequence and volume at the correct pressure is the goal of any fracturing treatment.
A fracture propagates until the fluid leak-off rate equals the total injection rate. It follows that by propagating a fracture with a non-penetrating fluid, leak-off will be minimized and length maximized. This is typically done by increasing fluid viscosity with gelling agents or by adding insoluble or slowly soluble materials that form a skin on the fracture face and inhibit leak-off. A hydrocarbon emulsion in water can also be used to reduce leak-off.
Following the fracture propagation fluid is the proppant transport fluid, which must have sufficient viscosity to carry the suspended proppant far out into the fracture, but must also be designed to revert slowly to a low viscosity fluid to permit easy return to the wellbore.
Depending on the size and type of fracture stimulation treatment, relative volumes of the penetrating fluid, propagation fluid, and transport fluid will vary. Typically, the penetrating fluid is approximately 1,000 to 2,000 gallons. The propagation fluid may approximate 30% of the total treatment, and the proppant transport fluid would comprise 65% of the fluid. The fluid used to flush the proppant-laden transport fluid from the wellbore should only be the capacity of the tubulars.
All of these fluids must be compatible with the formation rock and fluids. Emulsions formed by mixing fracturing fluids in formation oil can restrict permeability and recovery of the treating fluid. Minerals dissolved from the formation can react with the often complex chemistry of the viscosifying agents and gel-breaking agents. It is essential that fluid compatibility be confirmed prior to pumping and any additives required to achieve compatibility be included. A few of these are listed in your manual.
Although high viscosity is a desirable characteristic for an efficient fracturing fluid, one of the major expenses of a fracture treatment is the cost of renting the high horsepower equipment required to pump such a viscous proppant-laden fluid. The frictional losses encountered while pumping the frac fluid through the tubing or casing can contribute greatly to the horsepower requirements and costs. Typically, chemical additives are used to reduce frictional pressure losses while maintaining fluid viscosity.
Most of these gels are also very sensitive to temperature. High temperature additives or cool-down fluid pumped ahead of the fracture fluid can allow these gels to be used in high temperature wells without premature loss of viscosity.
The proppant and its correct placement are also critical aspects of a fracture treatment. Some would say the most critical, since the proppant enables the induced fracture to maintain the conductivity required to achieve an improvement in flow rate. There are a large number of different propping agents available, and each has an application for which it is best suited.
A good proppant has small, evenly sized, well-rounded spherical particles. The particles should have consistent density, high compressive strength, and should be insoluble and stable in reservoir fluids at reservoir conditions.
The most commonly used fracturing proppant is sand, typically from northern Illinois or southwestern Texas. Next are the high-strength proppants, such as sintered bauxite, followed by intermediate-strength proppants, such as fused ceramic material. The selection of the proppant is based on the closure stress that will be exerted by the formation.
Closure stress is the amount of force per unit area acting on the proppant and is essentially equal to the original pressure required to open the fracture, minus the pressure remaining in the fracture. The equation shows that with production, the closure stress increases as pressure decreases, and the stress is greatest near the wellbore, where the pressure drawdown is greatest.
The fracture conductivity will decrease if the proppant is embedded in the rock matrix or crushed. Angular proppant particles tend to crush more easily, hence the attractiveness of a proppant with a high degree of sphericity.
The larger the proppant diameter, the greater the permeability of the propped fracture, up to a point. However, the proppant must be sized to flow freely through the fracture during the treatment. Generally, a fracture width 2.5 to 3 times the maximum particle size is required. A common proppant is 2040 mesh sand with a particle size of 0.0331 to 0.0165 inches.
The selection of the appropriate propping material must consider fracture conductivity as it relates to downhole conditions. A proppant that is crushed will yield poor results. The force exerted on the proppant will depend on the area of the proppant contacting the fracture walls. One method of placing a value on fracture conditions is to determine the embedment pressure of the formation rock. An accepted technique measures the load that must be exerted on a steel ball of 0.05-inch diameter in order to penetrate the formation rock 0.0125 inches. Examples of embedment pressures are given for several formations. As shown, embedment pressures range from 20,000 to 450,000 psi. It is apparent that sand could be unacceptable as a proppant in formations with high embedment pressures.
The success of a fracture stimulation is measured after the well has been fractured and placed in production. The results of a fracture stimulation treatment are a function of many reservoir and treatment properties. It is imperative that the engineer understand these factors and consider what effect they may have on the treatment. The material covered in this section of the video, and much more, is discussed in your manual. Please read Section 1 before proceeding with the video and work the appropriate exercises. The preceding section of the video, which addressed fracturing history and theory, indicates the tremendous potential that fracture stimulation holds for many wells. However, not all wells will benefit economically from fracture stimulation. For example, an extremely tight formation may not be capable of commercial production even following fracture stimulation. Or, an undamaged prolific well may not realize any improvement in production following fracture stimulation. Wells that are candidates for fracture stimulation are wells that will yield an acceptable economic return or justify the development of an entire field.
The 4 basic types of reservoirs considered for hydraulic fracture stimulation are low permeability reservoirs, partially depleted reservoirs with permeabilities typically in the range of 1 to 100 millidarcies, reservoirs suffering from severe deep penetrating formation damage, and extremely heterogeneous reservoirs fractured in an attempt to connect more permeable reservoir sections with the subject well bore.
A low permeability formation is the primary type of reservoir that is fracture stimulated. A large number of oil and gas wells, even entire fields, are only capable of commercial production rates following fracture stimulation. Generally, a reservoir having an effective permeability of less than 1 millidarcy is termed tight and should be considered for fracture stimulation shortly after initial completion.
The other reservoir characteristics mentioned that may justify fracture stimulation can yield equally impressive results. Recommending a fracture stimulation for a well that will not benefit economically from the treatment can often be avoided by conducting the proper tests beforehand. For example, a pressure test would identify a well that is near pressure depletion and unable to produce hydrocarbons because of critical fluid saturations. In addition, a pressure test would indicate if the well was suffering from near wellbore damage, that could possibly be removed with a small matrix acid job.
Fracture stimulation of a well with poor reservoir properties with the goal of communicating with more productive sections of the reservoir is usually considered poor practice. However, if data exist that support fracture stimulation, the results could be impressive.
The data required to justify fracture stimulation may be easily obtained. The history of the subject area or decline curve analysis may indicate the need to fracture stimulate sometime in the life of a well. In most cases, however, well testing is recommended to justify the suspected need.
Pressure buildup or drawdown tests give excellent data that can be evaluated to determine the need for fracture stimulation. The value of a properly conducted pressure test is considerable. In addition to other information, reservoir pressure, skin damage, and formation permeability can all be determined. The result of a pressure transient test can justify the necessary remedial work or stimulation method that should be recommended.
Other means of obtaining important data should not be overlooked. For example, reservoir properties that justify fracture stimulation can also be determined from well logs or drill stem tests. Well logs are not as quantitative as pressure transient tests because of their limited radius of investigation. However, reservoir properties may indicate a low porosity, dense formation, which would appear to be a marginal producer at best.
A drill stem test evaluated in conjunction with well logs often yields a better indication of reservoir properties. Although considered a pressure transient test, a drill stem test does not always yield quantitative results. However, from a qualitative standpoint, it can be determined if a reservoir is tight.
Because of the marginal economic character of most wells considered for fracture stimulation, an unsuccessful frac job can be an economic disaster. Because of the potential downside, a proposed treatment must be based on sound engineering methods and judgment. Prudent selection of wells to be fracture stimulated is as important as the design and execution of the treatment. Now that we have discussed the methods used to determine if a well is a candidate to fracture stimulate, let's consider fracture treatment design.
The next step is to design the most cost-effective treatment. If the engineer is fortunate, case histories of fracture-stimulated wells in the subject reservoir will be available for reference. In any event, the engineer will want to base his stimulation design on one of the scientific frac models discussed in your manual. This does not imply that the engineer should ignore proven practices, but that scientific theory should be used in conjunction with proven field practices to design and understand the best possible treatment.
The object of fracture stimulation is to significantly increase the productivity of a well. The method for determining the possible productivity increase resulting from fracture stimulation should be an accepted method. The McGuire and Sikora method has proven reasonably accurate in reservoirs that are not severely damaged or naturally fractured. This method sees frac length as one of the most controllable factors in determining productivity increases resulting from hydraulic fracturing. The nonlinear relationship between frac length and productivity increase is the basis for cost-effective frac design. For example, using the McGuire-Sikora curve, an induced fracture with a conductivity ratio of 10 to the 4th and a frac length to drainage radius ratio of 0.5 would yield a 5.5-fold increase in production. If that same fracture extended all the way out to the drainage radius of the well, only a slight additional increase would be expected.
Another method to determine post-frac production utilizes dimensionless terms. This method, introduced by Agarwal and Carter in 1973, calculates dimensionless fracture conductivity, time, and production. Your manual explains this technique, which enables cumulative production and production rate to be determined theoretically at any point in time following the frac treatment.
If the desired productivity increase and drainage radius are known, a propped fracture length can be determined. In many cases, it may be impossible to prop a fracture the entire length of the well's drainage radius. And in fact, a fracture extending only a small percentage of the drainage radius could still yield a significant production increase.
Before computer design models can be run to determine the most cost-effective design, other frac dimensions, such as height and width, must be estimated. Under certain conditions, it is advisable to conduct a mini-frac or data frac on the subject well prior to designing the fracture stimulation treatment. Although the expense of this test may be significant, the data obtained may prove extremely valuable in designing the most appropriate treatment. This mini-frac technique is explained in your manual.
The dimensions of the induced fracture width can be estimated from an accepted frac model or from field tests, such as a downhole camera or impression packer. The downhole camera can yield excellent data in open-hole completions. This tool can be used in certain fluid-filled well bores. However, it is better suited to dry gas wells. Because of the limited availability of field tests, the frac width used in treatment design is usually based on a frac model such as the KGD or PKN models.
Frac height, an extremely difficult parameter to determine, can be based on special logging techniques that determine critical rock properties, microfrac data, known geological barriers, and post-frac height determination techniques employed on nearby wells. One or all of these methods should be employed to determine frac height for design purposes.
It should be noted that in practice, injection rate appears to affect frac height. For example, well A was fracture stimulated at 15 barrels per minute. Well B was fracture stimulated at 40 barrels per minute. Production following the treatment indicated that well B communicated with the underlying water-bearing zone. This was evidenced by the water production of 120 barrels per day versus 10 barrels per day from well A. Such increased injection rates often result in increased frac height, although this is not apparent from the various frac models.
Let's look at a typical fracturing treatment design program. Programs like this require limited input data and can indicate the relative aspects of the various design parameters and assumptions.
Data such as Young's modulus, Poisson's ratio, and the fracture geometry model are often based on empirical relationships or analogies with similar reservoirs. Porosity, bottom hole temperatures, and qualitative permeability can be obtained from well logs. Well bore radius and well spacing can be determined from drilling reports and field maps. Reservoir pressure data can be obtained accurately from pressure tests, pressure gradients, and several reservoir engineering techniques.
The input data concerning frac height is very important, yet is often the most difficult to predict. For each type of fluid system design, several models should be run using varying frac heights so that the effects of this factor are understood. Treatment data, such as viscosity and leak-off coefficients, refer to the properties of the fracturing fluid. These values are more appropriately assigned by the service company engineer, but should be discussed in detail. Various types of treatment design should be run to determine the most cost-effective stimulation treatment. These fluid designs may include systems consisting of cross-linked gels, foams, gas assists, or light gels.
The output from these programs for given fluid systems gives valuable data that can be compared, such as frac width, length, height, theoretical productivity increase, and treatment cost.
Now, at this stage, frac dimensions, proppant conductivity, and a fluid system will have been determined. The engineer must also consider wellbore hydraulics and tubular properties before a final frac design can be determined. It's possible that a fracture stimulation technique may not be feasible due to limitations imposed by the casing and tubing strings. So, an engineer should construct a wellbore diagram. The top of cement and annular pressures are extremely important and must be shown. Dimensions and strengths for all equipment should also be included. Often the weakest point during fracture stimulation is at the top of the cement behind the casing string or at the wellhead. Determining treating pressures must also include the dynamic conditions experienced during the frac. Friction losses can be great, requiring greater surface treating pressures, especially when treating through tubing.
The basic equation which must be understood is the surface injection pressure is equal to the bottom hole fracture pressure plus the frictional pressure drop in the pipe plus the pressure drop through the perforations minus the hydrostatic pressure of the wellbore fluid. This equation can be manipulated to yield useful information concerning rock and fluid properties.
For example, if the pumps are shut down during injection above fracture pressure, the bottom hole fracture pressure equals surface injection pressure, now called the instantaneous surface shut-in pressure, plus the hydrostatic pressure of the wellbore fluids. This enables an accurate fracture gradient to be determined.
Due to the information obtained by understanding wellbore hydraulics, it is strongly suggested that all fracs include a brief injection test prior to the fracture treatment. The fracture initiation stage, or breakdown, should be followed by an injection test. This consists of pumping fluid at a predetermined rate above fracturing pressure until injection pressure and rate have stabilized. Once stabilized, the pumps are shut down and the pressures recorded. These pressures can then be applied to the basic equation to solve for the unknown variables. It should be noted that the instantaneous shut-in pressure obtained during this test is often lower than the instantaneous shut-in pressure obtained following the fracture treatment.
As a result of this injection test, the number of perforations accepting fluid can be calculated. This is important since not all the perforations are likely to be open. Referring to the basic equation of wellbore hydraulics, it can be determined that 4 of the 5 variables are known or can be calculated. From our injection test, we were able to determine that the surface injection pressure was 1700 psig. The fluid being pumped was treated fresh water exerting a head of 1775 psig. A bottom hole treating pressure of 2911 was calculated for this 4100-foot well, and friction loss through the pipe was given as 7 psi per 100 feet, totaling 287 psig. Therefore, perforation friction loss equals 277 psig.
From this, the number of open perforations can be calculated using the equation where pressure drop across the perforations equals the density of the treating fluid in pounds per gallon multiplied by the pumping rate squared in gallons per minute, divided by the constant 8,090 times the area of the open perforations squared. Knowing that the perforations have an average entry hole with a diameter of 0.53 inches, it can be calculated that approximately 9 perforations are open. It should be noted that the constant of 8,090 is based on a perforation coefficient of discharge of 0.82.
The increase in friction loss and fluid density due to the presence of the propping material must also be considered. The effect of sand concentration on friction pressures is illustrated by this graph. At 4 pounds per gallon, sand would increase friction pressure by a factor of approximately 1.375. There are several methods used to adjust friction losses. It is suggested that the viewer be familiar with these methods through the service company and/or the references and further reading sections at the back of your manual.
The use of nitrogen or carbon dioxide as an additive to the stimulation treatment should be considered. These gases can be used in low volumes as a gas assist or in large volumes, creating a foam treating fluid. In many cases, the gas will greatly assist the cleanup of the well, reduce leak-off, and prevent formation damage. Other benefits of these gases are numerous and should be discussed in detail with the service company representative.
At this stage, we have determined the fracture dimensions needed to give the desired production results and what pressures the wellbore can withstand. The main consideration left is selection of propping material and chemical additives. Many factors must be considered in choosing the proppant material. Your manual discusses the uses and applications of these materials in detail. The most common proppants are sand, sintered bauxite, and intermediate strength proppants.
The proppant chosen must withstand any reservoir stress without crushing or embedment and be highly conductive and cost-effective. In most wells above 6,000 feet, a good quality sand is usually the most appropriate choice.
The ability of sand to serve as proppant is sometimes overestimated. Sand is a brittle proppant that can be severely crushed when the formation embedment pressure, closure stress, and proppant placement are not favorable.
The conditions to which the propping material will be subjected must be known in advance. It is emphasized that an inappropriate proppant may yield poor results.
Hydraulic fracture stimulation is often chosen as a final attempt to make a poor well or an entire field profitable. Often these reservoirs are of poor quality and contain clays, iron, and other potentially damaging material. Unless precautions are taken, severe damage to the reservoir or induced fracture may result.
There are many chemical additives that must be considered in the design of a stimulation treatment. Bacteria controls, clay stabilizers, scale inhibitors, sequestering agents, and surfactants are some of the more common chemical additives. The engineer is encouraged to become familiar with these chemicals and to discuss their proper use with the service company.
Damage can result from a reaction of the treating fluid to the materials in the formation rock or reservoir fluids. Therefore, chemicals often are necessary to ensure treating fluid quality and compatibility at reservoir temperature and pressure.
For example, tests have indicated that flowing fresh water through core samples containing clay material reduces permeability to near zero. This problem can be controlled with clay-stabilizing chemicals and potassium chloride.
So how do you determine what chemical additives are necessary?
Well, first the formation composition and fluid properties can be determined from well logs, well site geological reports, core samples, and fluid sampling of reservoir fluids. Then this information should be supplied to the service company so that they can run tests and propose a prudent chemical additive program.
It must be emphasized that a reservoir is characteristically very sensitive to changes in temperature, pressure, and chemical composition. A fracture stimulation treatment affects all of these conditions, so tremendous care must be exercised to prevent damaging results. And chemical additives are often very expensive. However, if costs must be reduced, cut back on total design volume, but do not cut back on justified chemicals. For a more detailed presentation of the material covered in this portion of the video, please read sections 2, 3, and 4 of your manual and work the appropriate exercises. We have reviewed the criteria generally considered necessary to design a successful fracture treatment. The next step is to prepare for the execution of the treatment. This involves all aspects from the physical placement of the necessary surface equipment through the systematic execution and monitoring of the job. A fracture stimulation treatment must be discussed in advance with field personnel and service company representatives. If considerations such as location size and equipment are not reviewed thoroughly with responsible personnel, the quality of the job may be seriously compromised. In some locations, the preferred treatment may not be possible due to location limitations. It is important that the engineer, service company representative, and field personnel also meet on location in advance of the job to discuss the treatment requirements. For example, the proper placement of the frac fluid tanks of sufficient volume, anticipated treating pressures, and safety concerns are all extremely important. Everyone must know their responsibilities and the proposed schedule.
On the day of the frac, the engineer should be on location early to review everything with field personnel and the service company frac operator. The on-site meeting to review the job is extremely important. At this time, all chemicals and pumping schedules should be reviewed. The service company's call sheet and the engineer's design should be compared and checked. Discuss pump capacity with the frac operator. Hydraulic horsepower requirements should have been agreed on at an earlier time, and it is usually requested that excess pump capacity be available on location in the event of any pump failures during the job. The engineer should review the surface and downhole equipment with the operator, making sure that the operator reviews his wellbore diagram. Everyone should be present during the pre-frac safety meeting and made aware of their responsibilities and of the maximum treatment pressures.
The safety aspects of a fracture stimulation treatment cannot be overemphasized. As shown in the staged line failure during a nitrogen assist fracture treatment, exceeding the design strength or improper makeup of equipment can have devastating results. The engineer should know the design parameters of the equipment being used and be sure that all connections from the wellhead through the pump trucks are secure. Unfortunately, not all failures are staged and accidents do happen. The engineer should act responsibly and place safety first. At this point, before the frac job begins, let's review all the equipment on location, starting with the frac tanks containing the treating fluid.
These tanks have a volume of 500 barrels. On level ground, it is generally assumed that 480 barrels may be pumped from a tank. However, on locations that are not level, or when high rates will be pumped from the tanks, causing air to be sucked into the lines, pumpable fluid may be less. During the fracture treatment, fluid is drawn from these tanks with low pressure lines into the blender. On the blender, chemicals can be mixed on the fly and pumped down hole or circulated back into the frac tanks during pre-mixing. The vessels used to transport the sand are positioned so that the propping material can be carried by conveyor to the augers, which send it to the blenders, where it is mixed with the treating fluid. The engineer should visually inspect the proppant material in the transport vessels. The frac fluid tanks and proppant storage facilities should be monitored throughout the job to ensure that the flow meters, which are usually located at the blenders, are accurately measuring injected volumes. From the blenders, the proppant-laden fluid is pumped into the pump trucks at low pressure. There, it goes through triplex pumps and is discharged at high pressures. The flow lines from the pump trucks to the wellhead are high-pressure lines connected with hammer unions. In this line, there is a densiometer, which transmits fluid densities to the frac monitoring equipment located in the frac van. The operator is in communication throughout the job with all members of the service company on location. Downstream of the densiometer is the wellhead. This wellhead is specially equipped with a tree saver or isolation tool, which will protect the wellhead from high pressures and erosion caused by the proppant. Following the treatment, this high-pressure equipment will be removed and replaced with equipment designed for the lower pressures that will be experienced when the well is shut in or producing.
The first step of the fracture treatment is to break down the formation. Only a very few perforations may be open at this stage. Therefore, a technique should be employed that will open as many as possible. One technique is to break down the formation using perf balls and acid. This technique allows successive stages of acid to reach all the perforations. Prudent perforating techniques presented in Video Library Module PE303 perforating should be reviewed and employed whenever possible.
Again, it should be emphasized that the pre-frac breakdown be initiated with acid as the penetrating fluid. Many formations will not break down without acid contacting the perforations.
Now that the formation has been broken down or fractured, it is time to conduct the injection test discussed earlier. This can be conducted with the pad fluid, so no special fluids are necessary. As long as the fluid density and friction loss gradient are known, any non-damaging fluid will do.
Following the injection test, a decision must be made as to whether or not sufficient perforations are accepting fluid. If an insufficient number of perforations are open, then a second stage of acid with perf balls is required. This will open additional perfs, reduce surface treating pressures, and allow better distribution of the fracture treatment into the formation. It should be defined in advance what is a sufficient number of open perforations, and what might be the perforation ball sealers and acid requirements for the job.
The perforation ball sealers should have a density greater than the treating fluid, so that when the perfs are backflushed, the balls will fall to the bottom of the well bore before the frac begins. In some instances, it may be suggested to install a perf ball catcher at the wellhead so that any perf balls produced during the flowback will not seat in the choke and shut the well in.
Now that the formation has been broken down and we have determined the bottom hole treating pressure and reviewed the wellbore hydraulics, we can begin the major portion of the fracture treatment.
If the service company is able to supply a treatment monitoring van equipped with a computer, this service should be used. The calculation of friction losses and fluid density can be very complex, especially when fracture stimulating with a foamed fluid or gas assist.
Some on-site computers can quickly generate a plot of differential pressure versus the log of time. This enables the engineer to determine which mathematical frac model, the PKN or KGD, is most applicable. Other information obtained can readily be used to predict fracture height growth and anticipate the possibility of a tip screen-out.
If the job is of sufficient length, on-site treatment redesign is possible. the computer is a powerful tool and should be utilized to its maximum capability. However, the engineer should be aware of the methods employed by the computer and be able to monitor frac performance without one. In fact, many frac treatments are conducted without the aid of the computerized frac van.
However, all major service companies supply a frac van with digital readouts of treating pressures, injection rates, and fluid volumes. A permanent record of this data is obtained on the pressure rate chart, or fracometer. Accurate calibration of this equipment is critical, so it must be tested prior to the frac.
The engineer should monitor this chart closely throughout the frac and be sure to make notes on the chart as necessary. Occasionally during the job, treating pressures may indicate potential problems. In the event pressures are increasing and approaching the maximum, what should be done?
Aside from safety concerns and damaging the tubulars, being unable to complete the job and ending up with a wellbore loaded with proppant is the worst scenario. If a screen-out appears imminent, often the first course of action is to cut the proppant. The resulting decrease in hydrostatic pressure of the wellbore fluids will then lead to an increase in surface injection pressures unless friction losses can be reduced. Lowering the injection rate will accomplish this. The next main concern is to clear the wellbore of propping material. Once cleared, the well should be shut in and the decision made whether or not to continue the job. In the case of a near wellbore screen-out, fluid could continue to be pumped in an attempt to open sufficient area to enable the frac treatment to continue. It is possible that the area could be flushed with fluid and the treatment continued. Care must be exercised not to displace the sand near the wellbore during the final stage of the treatment, since overflushing may cause the formation to heal entirely.
There are many options for reacting to a screen-out. The reasons for the screen-out, the type of treating fluid, the stage of the frac, and so on. They all must be considered before the most appropriate course of action is taken. The important fact to consider is that not much time is available to review the situation. Therefore, the various contingencies should be discussed prior to the job.
The possibility of screen-out problems is a good reason to have excess treating fluid on location. Often this fluid would not need to be pre-mixed with all the design chemicals, since many could be added on the fly. Your manual discusses other important considerations in frac execution. You should read the text carefully to become acquainted with some additional scenarios. The key to professionally supervising a fracture stimulation treatment is understanding what may be happening and being prepared for deviations from the design.
The physical aspects of fracture stimulation have been completed. There remains considerable post-frac evaluation that can be conducted to further understand the characteristics of this well and to consider stimulation improvements that may be incorporated into subsequent treatments on similar or nearby wells. If it was decided that post-treatment fracture height determination would be necessary, now is the time to conduct such tests. As discussed in your manual, there are two generally accepted tools to determine frac height following the treatment. These tools are temperature logs and radioactive tracer surveys.
The temperature survey is conducted shortly after pumping has ceased and measures the drop in bottom hole temperature due to the cooler fracturing fluids. Deviation from the regional temperature gradient, as shown on the example log, indicates the approximate frac height near the wellbore.
Radioactive tracer surveys have proven equally successful in determining near wellbore fracture heights. This method involves the placement of radioactive isotopes at various stages of the frac and the use of a gamma ray log to define the fracture height. Often the radioactive material is placed during the final stages of the job to highlight the fracture. However, as shown by this model, the isotope placement in the fracture does not always indicate near wellbore conditions. In light of this, it is advisable to place the radioactive material in various stages throughout the job.
Whichever post-frac survey is used to determine frac height, care must be taken that the wellbore is essentially free of residual propping material before conducting such tests, since these tools can get stuck relatively easily.
Immediately following the frac, a record of shut-in pressure and time will give extremely valuable data. This data can be easily gathered by installing a pressure recorder at the wellhead. A technique presented by Nolte and Smith to analyze the shut-in pressure following the treatment will quantify several fracturing parameters, such as closure pressure, closure time, fluid loss coefficient and efficiency, Young's modulus, and fracture length.
Following the completion of any bottom hole survey and the removal of fracturing equipment, the well must be prepared for flowback. The shut-in time necessary to allow for formation closure can be based on a closure time as determined from the Nolte-Smith method, or on what is accepted as appropriate for the subject area. Generally, 24 hours is considered sufficient to allow the formation to heal and prevent excessive return of proppant to the surface.
While on location, the engineer should discuss the flowback procedure with the field supervisor to ensure that flowback performance is monitored and samples of the flowback fluid are taken. Monitoring of the fluids returned after the frac is extremely important. If possible, the well should be flowed into tanks or a pit of known volume.
The percentage of fracturing fluids returned to the surface is often indicative of the degree to which the treating fluids damage the reservoir. If recoveries are low, 75% or less, then treatment with different fluids should be considered, since the fluids that remain in the formation could reduce the relative permeability of the reservoir hydrocarbons.
Samples of the fluid should be collected as they are recovered. Evidence of proppant, crushed proppant, scale, clays, and so on can indicate potential problems that should be addressed in future jobs. The viscosity of the flowback fluid can indicate the success of a properly designed gel system. Viscosity of treating fluid in excess of 1 centipoise during flowback can be extremely damaging to the propped fracture and possibly jeopardize the entire job. In addition, water salinity should be measured and compared to known formation water to enable a more accurate assessment of pumped fluid recovery.
Often a restrictive flowback through a choke is preferred. Variable chokes are necessary since the choke usually has to be adjusted throughout the flowback to prevent excessive drawdown or to maintain a desired rate. Care must be taken to prevent damage to the choke from proppant production. The rate at which a well should produce immediately following the frac should be discussed beforehand with the service company engineer.
We've addressed several aspects of the field process of gathering post-frac data. Now, let's leave the well site and see how to evaluate this data and determine the success of the job over the long term. We have designed the frac based on a fracture growth model. It's time to compare actual treatment pressures to the pressures our chosen model predicted. The pressure response throughout the fracturing procedure will have yielded data that can be used to define many previously assumed reservoir properties. The PKN and KGD models must now be compared to actual treatment pressures.
In reservoirs where the PKN model is correct, the surface wellhead pressure increases due to friction losses experienced in the fracture.
In reservoirs where the KGD model is more applicable, the surface treating pressure will decrease during the treatment because of a reduction in friction pressure within the fracture as the width is increased. In each case, correction of surface pressure to bottom hole pressures must be made, based on factors such as sand concentration, pumping rates, and so on. Other factors that can affect surface treating pressure are partial proppant screenouts, plugged perforations, and reservoir heterogeneities.
On many jobs, the service company supplies an on-site computer to calculate the friction pressure losses and the hydrostatic pressure of the slurry in order to more accurately determine the bottom hole fracturing pressure. The changes in the bottom hole fracturing pressure are recorded, and a plot of differential pressure versus the log of time is prepared as the data becomes available. The most applicable fracture model can be determined from this plot. Choosing the right frac model is extremely important in designing a treatment and in evaluating expected post-frac productivity. Future design parameters for entire fields may be dependent on this information.
The long-term post-frac analysis includes pressure transient tests, decline curve analysis, comparison of case histories, actual versus projected recoverable reserves, and economic evaluation of fracture technique.
A pressure transient analysis technique presented by Agarwal, Carter, and Pollock is a generally accepted method using type curves to compare post-frac production with that projected using a mathematical simulator. You are strongly encouraged to familiarize yourself with the application of these type curves.
Decline curve analysis is particularly valuable in determining productivity increases resulting from fracture stimulation of older wells. These curves showing production rate versus time on semi-log paper are standard data compiled throughout the economic life of a well. Productivity increases due to fracturing can be readily obtained from these curves.
Once it becomes apparent what percentage of the productivity increase is due to fracture stimulation, computer models predicting post-frac productivity should be rerun. By eliminating the unknowns, especially productivity increase, a reasonably accurate assessment of reservoir conditions controlling fracture stimulation can be made.
Ideally, other wells have been fracture stimulated within the same field using various fracture stimulation techniques. After consideration of factors unique to individual wells, the production history of each well should give a good indication of which frac technique is the most successful. Fracture stimulation has more often been considered an art than a science. This is presumably because of many uncertain factors affecting stimulation results. Currently, considerable effort is being made to understand and calculate projected performance. Therefore, the engineer is encouraged to utilize new technology to find out not only which technique is the best, but why. This material is covered in more detail in your manual. At this time, please read Section 5 and complete the exercises. Good luck.